Okay. Okay, then so in the last class, I think we have solved this problem, right? Okay, so in that we have seen right. So this kind of circuit we have observed, and we tried to calculate what is the active power consumed by all the three passive elements shown here, and also average power supplied from each source. Okay, and we have observed that the average power consumed by inductance or capacitance is 0. Okay, average power is 0. Instantaneous power may not be 0, it is a time varying function. Okay, right. And we observed at the end that the power supplied from the left hand side source, that is 20 volts, is 50 watts, right? And the power absorbed by resistor is something like 25 watts, and the power absorbed by right hand side source, which is 10 volt source, is also 25 watts. That means 50 was delivered and 25. Yeah.
Sir,
Yeah.
we can't see the screen.
Sir,
You are not able to see my screen.
Sir, only
yes, sir.
WebEx screen.
So WebEx screen only we are able to.
Okay, okay, wait. I will come back. Now you are able to see?
Yes, sir.
You are able to see, right? Okay, okay. So you are able to see that P 10 volts is equals to minus 25 watts.
Yes, sir.
Okay, okay then. So this is what we have seen. So the source has supplied 50 watts, 20 volt source, and 25 watts was consumed by resistor, and remaining 25 watts is actually going into the 10 volt source. That's what we have seen, and we concluded that the average power absorbed by inductance or capacitance is 0. Okay. Now we will start discussing regarding effective value of current or voltage. Okay, so what is this effective value? Till now we have seen in maximum value of voltage or current, which is represented as Vmax or Imax. Okay, so now we'll see what is this effective value. So if you see in India, what is the voltage for a single phase voltage value which is coming to your house? Can anyone say?
230 volt.
Okay, so 230 volts is a voltage which is coming. So whether it's an instantaneous value or not.
Sir, maximum value, sir.
It's maximum value. Okay, right. So let's see whether it's maximum value or not. So in general, the voltage which is coming in India to a single phase system is 230 volts, and the frequency is 50 hertz. If you observe that, it is not a maximum value or not an average value also. It is neither instantaneous value also. Okay, so it is not an instantaneous value, because if it's an instantaneous value, it should vary with respect to time, and you can't say it is 230 volts. And it is not maximum value also. Okay, not maximum value or amplitude. It is not maximum value or amplitude. So what is this 230 volts is called as? Okay, this 230 volts is the effective value of this sinusoidal voltage, any sinusoidal voltage. Okay, if 230 volts is told, then it is called as effective value. There is one more name for effective value also, that we'll see later. Okay, what this says is, this is a measure of the effectiveness of a voltage source in delivering power to a resistive load. Okay, so it is a some kind of measurement for a voltage source. Okay, right. So if you have a voltage source, how effective it is able to deliver power to a resistive load. Okay, because resistive load only will consume power. So if you consider a resistive load, how effectively your voltage source is able to deliver power to that. Okay, So that indication we can get from this effective value. Right. So effective value is nothing but it is the measure or it is an indicator which is giving us information that how effectively our source is able to deliver power to a resistive load. Okay. So this 230 volts which is shown in India for single phase system is called as effective value. Okay. So this is not the maximum value or this is not the instantaneous value. This is effective value. Okay, so how to measure this effective value if you have a sinusoidal voltage or a current? Okay, so effective value for a periodic waveform. It can be a sinusoidal voltage or any periodic waveform. You can apply this method for finding this effective value. So what it states is effective value of any periodic current. I am considering current. Okay, voltage also it will be the same thing. The effective value of any periodic current is equal to the value of the direct current which flowing through an R ohm resistor delivers the same average power to the resistor as does the periodic current. So what it states is if you have an R ohm resistor, okay, and you want to find out the effective value of some periodic current, okay, so what you have to do is you allow that current, right, allow that current to pass through that resistor and find out the average power. You can calculate average power. Na? You have current, so I effective, I mean I max square into R divided by 2, that will give you the average power. Okay, calculate that average power and you send direct current also through the same resistor such that the average power or the average power produced by the direct current and the average power produced by periodic current should be same. When both are equal, at that instant your direct current and your effective value of the periodic current are same. Okay, you may get little bit confused with this, but the statement says that the effective value of any periodic current is equal to the value of the direct current which flowing through an R ohm resistor delivers the same average power to the resistor as does the periodic current. Okay, right. I am explaining the same statement in 2 steps. Okay, below. So from this you will get clear picture. Okay, so what it states is, in other words, we allow a given periodic current to flow through the resistor. Okay, so periodic current is you are sending through some resistor. Okay, determine the instantaneous power. How to calculate? I max square into R, right? I mean the instantaneous power will be I square into R, that's all. This is instantaneous current, na? So I square into R, that will give you instantaneous power, and then find the average value of that by integrating over one time period. Okay, right. So you have calculated the average power and kept it aside. Okay, then second step what it says is we then cause a direct current to flow through the same resistor. Okay, consider the same resistor and allow the direct current to flow through that resistor and adjust the value of the direct current. Direct current is nothing but DC current until the same value of average power is obtained. Okay, so from this step, okay, you have got some average power after calculating and you adjust the value of the direct current such that same average power is delivered to the resistor also by using DC current. The resultant magnitude of the DC current is equal to the effective value of the given periodic current. That means in that scenario, whatever the DC current which is flowing, such that the same power is produced as produced by the periodic current. So that instant, that DC current magnitude is nothing but the effective value of your periodic current. Did someone get some idea regarding this or not?
Yes, sir.
You are able to understand it, right? That means you take a periodic current
Yes, sir.
and send it through some R ohm resistor, find the average value of power consumed by that resistor. Okay, you can find instantaneous power I square R and then integrate over one time period. You will get some average power when you are sending periodic current. Okay, next what you do is take the same resistor and send DC current through it. Okay, and adjust the value of DC current such that the average power which you have already noted. So that same average power should be shown with DC current also. Okay, right. That means nothing but VDC into IDC or IDC whole square into R. Okay, that's all. So that when the two powers are equal, at that instant, your DC current is nothing but your RMS value of the periodic current. Okay. Same thing I have shown in the circuit for your better understanding. So what it states is, this is the first case when I am considering periodic current. That means a sinusoidal function, let's say. Okay, so I have voltage V of t and current I of t is flowing, and I have a resistance R. Okay, so what will be the average power delivered to the resistor by this periodic current? First of all, instantaneous power is I square into R. Okay, if you are integrating over one time period, that is nothing but your average power. Correct na? So average power P is R by T integral 0 to T I square of T with respect to dt. This is the average power delivered to R ohm resistor by sinusoidal current or some periodic current. Okay. Next, second part is consider the same resistor, apply a DC voltage. Okay, so this is a DC source, something like battery. Okay, so I am sending this through the resistor R, and I will adjust the value of V E effective such that I effective square into R should be equal to this value, this average power. I will adjust such that. Okay, when the both are equal, simply I will calculate I effective square into R. That's all. So this is the power delivered by the DC current for the R ohm resistor. This is the average power delivered by a periodic current through R ohm resistor. Okay, right. So to get effective value, what I should do? These two powers are actually equal. This P and this P are equal. So that is the condition which you should satisfy to find out the effective value of the periodic current I of T. Okay, right. So try to equate these two and give me the value of I effective in some expression. You understood, na?
Yes, sir.
Okay, so give me the expression of I effective in terms of R, T, whatever it may be.
Square root of
1 upon 2.
uh,
1 upon t, the integration from 0 to t I square dt, and this should be under root, sir.
yes, sir.
Okay. So that means you have to simply equate the power P on the left hand side and the power P on the right hand side on your screen. Okay. So if you are equating those two, okay, then you can find the I effective, which is the DC equivalent current in terms of the periodic current I of t. Right. So I effective is root of 1 by t integral 0 to t I square of t with respect to dt. Okay. So everyone understood this or not?
Understood, sir.
Yes, sir.
Okay. If anyone has confusion in this,
Yes, sir.
please let me know. Okay. Right. So that means the average value, effective value is nothing but if you send the DC current to that, and same power should be delivered to the resistor with DC as well as with AC periodic current. So at that scenario, we will equate the two powers and we will get an effective value of current. Okay, right. So this is a measure of how effectively you are transferring power to your load, or power is delivered from the source. Okay, right. So this effective value is also called as RMS value. Okay, RMS means root mean square value. Okay, because if you see from this expression you are calculating the root of mean of square of your periodic current, right? So that's why it is also called as RMS value or root mean square value of current. Okay, right. So for voltage also it's the same scenario. So you will get the same expression even if you are calculating the effective value or RMS value of voltage. Okay, this is valid for any periodic waveform, not only sinusoidal waveform. Okay, right. Okay, so let us calculate the effective value of a sinusoidal current waveform. Okay, so I am considering periodic current I of t is given as Im into cos of omega t plus phi. Okay, so try to calculate the RMS value for this periodic current. You know how to do that, right? We have seen just now the expression I effective is root of 1 by t integral 0 to t I square of t with respect to dt. So simply substitute I of t, what I have given here, in that expression and try to solve it and find out the effective value of your periodic current. You are trying to solve it, right?
Yes, sir.
Okay.
Sir, it is 0, sir.
0. Please check one more time. Okay.
No, sir. Sorry, sir. Sorry, sir. Sorry, sir. Sorry, sir.
Okay. Hey, everyone, please try to do that. Simply substitute I of t function in the previous expression. Okay. So root of 1 by t integral 0 to t I max square cos of omega t plus phi with respect to dt. So you have to do that. Omega is equals to 2 into pi into f. Okay. So and f is equals to 1 by t.
Sir.
Yeah.
Sir, Im square by 2.
Im by root 2.
Im square by 2.
Im square by 2. That is equals to
Sir,
effective or I effective square.
yes, a square root of that.
Okay.
That is Im by root 2.
Okay. So I is equals to I maximum by root 2 you will get, or I of t whole square is equals to Im by 2 you will get. Okay. Im square by 2. Okay. Let's see that. Right. So what will be the t here? Omega is equals to 2 into pi into f. Okay. F is 1 by t. So from that you can calculate t value. Right. Omega is equals to 2 into pi into f. If you are calculating f is equals to 1 by t and substitute that, you are going to get t is equals to 2 pi by omega. Right. Your limits is between 0 to t, right? So you should have 2 pi by omega. Okay. So then you have to substitute that current in this expression and you have to solve this. Okay. So this is simple mathematics only. So root of 1 by t integral 0 to t I max square into cos square omega t plus phi, which is nothing but this I of t function. Okay, so you are integrating between 0 to time period t. So what will be that? T is equals to 2 pi by omega, right? So if I substitute that, it will become like this, and t is 2 pi by omega. You are substituting another limits, and I max square. So I max, I got it out. So cos square theta. So what formula you have to use? Cos 2 theta is 2 cos square theta minus 1, right? So from that you will get this value. Okay, clear? So 1 plus cos 2 omega t plus theta 2 phi divided by 2. So you'll get that. Now if you substitute, if you integrate and substitute your limits, right, this second term will, right, it will become 0, and you will get this t and 2 pi by omega. So you will get Im by root 2. Okay, so I effective is I maximum by root 2. Okay, for a sinusoidal current. Okay, is it clear to everyone?
Yes, sir.
Okay, if you have a doubt, you simply, do it slowly, do this integration. Okay, so 1 by 2 it will be a constant, so you will get a t here, and for this, okay, if you substitute your limits after integration, you will get the second term to become 0. Okay, right, so 2 omega by 2 pi into 1 by 2, so omega by 4 pi will be there, and t will be available. So limits 2 pi by omega and 0 you have to substitute. So after that you will get Im by root 2. Okay, so I effective is nothing but I maximum by root 2, right? You might have studied this in terms of RMS value. IRMS is I maximum by root 2. Okay, right, so both RMS value and effective value mean the same. Okay, so this is your effective value or RMS value for a sinusoidal current. For sinusoidal voltage also it will be the same thing, which will be Vm by root 2, right? So therefore the effective value of a sinusoidal current is a real quantity which is independent of the phase angle and numerically equal to 1 by root 2. That means 0.707 times the amplitude of the current. Okay, so the effective value is 0.707 times your maximum current Im. Okay, so now we have already seen the average power formula in terms of maximum value for a resistor, right, which is Imax square into R divided by 2. We have already seen this. Okay, right, so now you have the option of converting this maximum value into effective value or RMS value. So if you do that, power P is equals to I effective square into R. Okay, simply substitute I max value in this above expression. You will get power is equals to I effective square into R. Okay, so you can use either this one or this one, any formula you can use. The other power expression we have seen, right, which is the first term Vm Im by 2 into cos of theta minus phi. If you remember, in the past we have seen the average power is Vm Im by 2 into cos of theta minus phi. Okay, right, so if you write that Vm Im by 2 as Vm by root 2 into Im by root 2, then you can get the power expression as V effective into I effective into cos of theta minus phi. Okay, nothing but Vrms into Irms into cos of theta minus phi, or V effective square divided by R. Okay, so any of these formulas are valid and you can use any of these things to calculate the average power for a resistor. Okay, is it clear?
Yes, sir.
Okay, so simply we are substituting the effective value in the previous expressions for power which we have already seen. Okay, that's all. Right, remember this expression, P is equals to V effective into I effective into cos of theta minus phi. Okay, V effective is nothing but Vrms, I effective is nothing but Irms. Okay, so this is the single phase power which is very frequently used. Okay, right, so this capital P always indicates average power. Okay, and small p indicates instantaneous power. So this is average power formula. Okay, So next is, in the sinusoidal steady state, the phasor voltages and currents may be given either as effective values or as amplitudes. The two expressions differ only by the factor √2. Okay, so till now we have seen phasor voltage, which I have given as Vm at an angle of theta. Okay, phasor voltage we have already seen, Vm at an angle of theta I have given. Okay, so phasor can be expressed in terms of amplitude or in terms of RMS value. Both are correct. Okay, but one should clearly specify whether it is RMS representation or maximum value representation. Okay, so for example, if you see phasor voltage V, some voltage is there. So phasor voltage V I have given as 50 at an angle of 30 degrees. Right. So in amplitude I am saying, that means this 50 indicates the maximum value of your voltage waveform. Okay. If I want to represent in terms of RMS value, I can write the same thing as 50 divided by √2. Okay, because this is RMS value of your voltage at an angle of 30 degrees. So then it will be 35.4 at an angle of 30 degrees in RMS value. That means phasor can be represented in terms of amplitude or in terms of RMS value. Both are correct. But generally, people will represent with RMS value. Okay, there is nothing wrong if you represent with maximum value or RMS value. Okay, both are correct. But one should clearly specify whether they are representing in RMS or they are representing in amplitude. General standard is everyone will represent in RMS. Okay. Right, but in this course, if I am representing in RMS value, I will clearly specify. If I am representing in maximum value also, I will clearly specify. Okay, right. Okay, so till now we have seen what is called as instantaneous power and what is called as average power and what is called as RMS value or effective value of sinusoidal current or voltage, and we have seen the average power expression in terms of this effective values also. Okay, so there is one more power terminology in AC circuits, so that is called as apparent power. Okay, so what is this apparent power? We will see that. Okay, so if you assume the general voltage expression V of t in time domain and current expression I of t in time domain, they are given by this: V of t is equals to Vm into cos of omega t plus theta and I of t is equals to M into cos of omega t plus phi. The average power expressions are Vm Im by 2 into cos of theta minus phi or V effective into cos of theta minus phi. Okay, now apparent power is, it is defined as the product of V effective and I effective. Okay, so that means the product of Vrms and Irms is called as apparent power. Okay, and the unit for apparent power is volt amperes. Okay, because you are simply multiplying voltage and current. Okay, so that's why the unit is volt amperes. What is the unit for average power?
Bolt. Watt.
Watt. Okay, so the unit for average power is watts, and the unit for apparent power, which is nothing but the product of RMS value of voltage and current in a circuit. Okay, so that is apparent power and the unit is volt amperes. Okay, next, power factor. Okay, so if you see cos of theta minus phi, okay, can have a magnitude greater than unity. Okay, right, cannot have a magnitude greater than unity because cos of theta minus phi, the cos maximum value is 1. Okay, and it will be less than 1, it can be greater than 1. So the average power or the real power magnitude can never be greater than apparent power. Correct na? Right. So average power is given as V effective into cos of theta minus phi. So cos of theta minus phi maximum value is 1 and minimum value is 0. Okay. So if you see that apparent power, which is given as V effective into I effective, will always be greater than your average power, or at max both can be equal. Okay. Right. So cos of theta minus phi cannot have a magnitude greater than unity. So average power magnitude can never be greater than apparent power. Okay. So from these two terms, average power and apparent power, we can determine power factor also. Power factor of a circuit or an element. Okay. So what is that? Power factor, the ratio of average power to the apparent power is called as power factor. Okay. Right. So power factor is defined as average power divided by apparent power, which is nothing but P divided by V effective into I effective. Right. So power factor is equals to cos of theta minus phi. Okay. Correct. So average power, different terminologies are there for average power. All are mean the same. Okay. Average power, real power, true power, or active power. All are same. Okay. You can call it as a real power, you can call it as an active power, you can call it as a true power or average power. All mean the same. Okay. Right. And power factor is equals to average power divided by apparent power given as cos of theta minus phi for the considered voltage and current. Okay. Is it clear to everyone?
Yes, sir.
Okay.
Yes, sir.
So apparent power is nothing but V effective into effective, and cos of theta minus phi is nothing but your power factor, which is given as the ratio of average power to apparent power in any circuit or element. Okay. Right. So the unit for apparent power is volt ampere. Unit for average power is watts. Okay. Okay. So some conclusions we will derive from this. Okay. Unity power factor. So what kind of load will have unity power factor?
Resistance, pure resistor.
Okay. Only pure resistor can have unity power factor. Okay, let's see that. For a pure resistive load, the voltage and current are in phase. Okay, so that means theta minus phi is 0. Okay, so cos 0 will be equals to 1 and the power factor is unity. In other words, the apparent power and average power are equal. Right. So for a pure resistor, if you talk, the average power and apparent power are going to be equal because cos 0 will be equals to 1. Okay. Next, unity power factor can also be achieved for loads that contain both inductance and capacitance if the element values and the operating frequency are carefully selected to provide an input impedance having a zero phase angle. So what it means? Along with resistor, we have seen already one RLC circuit in the past. Okay. Along with resistor, you can have inductance and capacitance also in the circuit. Even in that scenario, you can have unity power factor for the circuit. Complete circuit can have unity power factor. When that is possible means you should have the inductive reactance and capacitive reactance and the frequency such that your inductive reactance and capacitive reactance will cancel out each other and only resistance will be present in your circuit. Okay. In that scenario, it is possible to get unity power factor. Even though the circuit is a combination of R, L and C, okay, if the L value and C value are such that your inductive reactance and capacitive reactance values are equal, that means XL is equals to XC. Okay. In that scenario, your impedance, if you calculate R plus J into XL minus XC you will get. Okay, when XL and XC are equal, then your imaginary term will become 0 and your net impedance will have only resistor. In that scenario, it is possible to get unity power factor even though the circuit is an RLC circuit. Clear? Right. So even an RLC circuit can have a unity power factor based on inductive reactance and capacitive reactance should be equal. Okay. Right. So this is regarding unity power factor, how you can achieve in a circuit. Next, zero power factor. So when you will get zero power factor,
So when there is no
Purely
resistance,
inductive and resistive.
90 degrees.
purely inductive and
Capacitance.
okay. So if you have only inductor in your circuit, okay, in that scenario you can get zero power factor. Okay. Or if you have a pure capacitor also, you can get zero power factor. Okay. A purely reactive load, that is one contains no resistance, that means no resistance is there, will cause an phase angle between the voltage and current of plus or minus 90 degrees. Okay. In that the phase angle difference will be can be plus 90 degrees or minus 90 degrees. Okay. In that scenario, the power factor is 0. Okay. So you can get zero power factor only for reactive loads which has zero resistance. Okay. Next, between 0 and unity power factor. So between the two extreme cases which we have seen just now, there are general networks for which the power factor range from 0 to unity. Almost all circuits mostly will deal, generally available in practical systems are having a power factor between 0 and unity. Okay, so generally they will be between 0 and unity. Okay, right. So we have seen the power factor can be 0 if you have inductive load or if you have a pure capacitive load. Okay, so how to differentiate whether it's inductive or capacitive? Both will have power factor of 0 value, but we should say now whether it's inductive nature or capacitive nature load. Okay, right. So for that, what they have given? They have given two terms. One is leading, and the one is lagging. Right. The ambiguity in the exact nature of the load. Okay. Power factor is 0. That is agreed. But I should specify what is the nature of the load. Okay. So this nature of the load is resolved by referring to a leading power factor or a lagging power factor. Okay. Right. So the term leading or lagging refers to the phase of the current with respect to the voltage. Okay. So that means even if you have zero power factor, to clearly specify because of which element I got zero power factor. Okay. There are two terms which were defined, which is called as leading and lagging. Okay. So leading power factor or lagging power factor. Okay. And this leading and lagging is basically the difference in the phase of the current with respect to the voltage. That means with your voltage reference, if your current is leading with 90 degrees, then you are having a power factor of 0 value and the nature of the load is leading. Okay, so current is leading. Next, if you have for a reference voltage, your current is lagging by 90 degrees, then your power factor is 0 and the nature of the load is inductive. Okay, right. So inductance will create 0 power factor. Okay, with the current lagging the voltage. Capacitor current will lead the voltage. Okay, so is it clear for all of you with regards to all these terminologies? Unity power factor, zero power factor, lagging and leading loads, inductive nature load, okay, capacitive nature load, okay, and apparent power, average power. Right. Is it clear to everyone?
Yes, sir.
Yes, sir.
Okay. Okay, so these all these terminologies are important because in the question they will ask like this only: what is the power factor? What is the nature of the load? Whether it's lagging or leading, you have to say. Okay. So when you say the power factor, let's say 0.6, you should say whether it's lagging or leading also. Okay. Right. So let's see that with some example.
Sir,
Yeah.
sir, previous
Great.
slide.
Yeah.
Sir, in the last, sir, leading or lagging, we can't say with the reference of voltage with respect to current.
No. So you have two terms, right? Power factor is zero, let's say whatever it may be power factor. So I have to say what is the nature of the load. Okay. Right.
Okay, sir.
So for that nature of the load, when I say you are getting power factor is, let's say 0.6. Okay. Okay. So whether it's a resistive load or not, you can say or not. If I get power factor is equal to 0.6, can you call it as a resistive load? I mean pure resistive load or not?
No, sir.
No, you can't call, because when pure resistor is there, you have power factor of 1. Okay. Now you are saying that the power factor is 0.6. Okay. So that means along with resistor, some other element is there. Okay. So it can be an inductance or it can be a capacitance. Okay. Right. So that's why you have got post 0.6. Okay. So now you have to clearly specify whether it is inductive. You have because of inductor in the circuit you got 0.6, or because of capacitor you have got 0.6. So that's why they have given two terms. One is leading, another one is lagging. Okay. So that means if you have a capacitor, you will have current leading. Let's say voltage is my reference waveform. If I have a capacitor, current will be leading or lagging?
Sir, leading.
Leading. So current will be leading. Okay. So current will be ahead of your voltage reference phasor. Okay. Okay. So that means because of R and C in your circuit, you are getting 0.6 power factor, and because of the capacitor, you are giving a term called leading. So that means if I say in the question, it has a leading power factor of 0.6. Okay, so that means you should understand that you have resistance and capacitance in your circuit. Okay, so the meaning is that. Is it clear?
Yes, sir.
If I say 0.6 lagging power factor load, okay, that means the power factor is 0.6 and lagging power factor. That means some inductor is present in your circuit. Okay, right. So this leading and lagging we will call the phase of the current with respect to the voltage. That means voltage is your reference phasor, and with respect to that voltage reference phasor, current may be leading, then you will call it as leading power factor. Current may be lagging, then you will call it as lagging power factor. Is it clear?
Yes, sir.
Okay. Okay. So we'll see one example. From that you will get better picture. Okay. So it's a pretty simple circuit. We have already seen complex circuits more than this. Okay. But here the objective is to find out the powers and understand what are the powers. So that's why we are considering this small circuit. Calculate the values for the average power delivered to each of the two loads. So we have two loads here. One is 2 minus J1 ohms and the one is 1 plus J5 ohms. Okay. So they are asking us to calculate the average power delivered to each of the two loads. And next, the apparent power supplied by the source and the power factor of the combined load. Okay. So there are three parts in this question. First, they are asking us to calculate the average power delivered to each of the two loads. Okay. So try to calculate this. You have the voltage, you have the impedance, you can calculate the current. Okay. So once you know the current, you can use the formula V effective into I effective into cos of theta minus phi to calculate power delivered to one load. Next, same formula for power delivered to second load also. Okay, so try to solve this. First calculate the equivalent impedance, next calculate the current. From that we can get the phase angles and magnitudes or RMS values of voltage and current. Then you can use the basic formula which we have discussed. So you got some mail from students or what? And no, I am already in class. 2 hours class today. Okay, okay. You have sent already mail, right? Okay, okay, okay. Okay, okay. Okay, okay, okay. Okay. So, did anyone try to find out the current?
36 minus 48J.
What is that? That is current.
Yes, sir.
Okay, so try to convert into polar form also because you want the angle, na? Okay, because to
Yes, sir.
calculate power we require current phase angle. So try to convert into polar form also. What is the equivalent impedance? Z?
3 plus 4J.
Yeah. Okay, straight away adding these two, you can get 3 plus 4J.
Yes.
Okay, let's see that. So the equivalent impedance is simple addition of the two loads which are shown here. So it will be 3 plus J 4. Okay. Next you have to calculate current. So IS. So in this circuit I have represented with IS, source current. So IS will be Vs divided by this Z. Okay.
So 12 at an angle of minus 50.
Okay. So it is 12 at an angle of minus 53. So simply you have to divide your 60 at an angle of 0 degrees divided by 5 at an angle of 53.13. So you'll get this value. This is your source current. So that means this is the current which was delivered from the source. Now they are asking us to calculate the average power delivered to each of the two loads. Okay. So the average power delivered to 2 minus J1 ohms you have to calculate. How to do that? First, to do that, you have to first find out the voltage across that particular element. Okay, right. So because when they are asking us to calculate the average power across any particular element or load, you have to find out the voltage across the element or load and current flowing through that. So you have to multiply these two only. Okay. So what is voltage V1? RMS value, because in the question 60 volts is given as RMS value. Okay. So voltage RMS V1 is equals to simply IS into Z1, which is nothing but this 2 minus J4. Okay, 2 minus J1. So try to do that. You will get V1 is equals to 4.8 minus J26.4. Did anyone got this or not? Or you have not calculated V1 at all? Try to do that and get the value of V1.
Yes, sir. Yes, sir. Got.
Okay, so simply you are multiplying the phasor current IS with impedance Z1, which is 2 minus J1. Okay, so 2 minus J1, if you convert into polar form, you will get like this 2.23 at an angle of minus 26.56. Okay, so simply if you multiply that, you are going to get voltage V1. Okay, because in the question they have asked to find out the average power for load 1. So that's why you have to calculate voltage V1 also. Now, what will be the value of power P1? I mean, consumed by this load 2 minus J1. How to do that? Can anyone say what is the average power consumed by 2 minus J1 ohm load? What is the basic formula you have to use for
V1
this?
IS
half into Vm into Im into cos theta minus phi.
Okay, so that is one formula. Another formula in terms of effective value,
sir,
can you
here-
say?
V1 V effective into I effective.
Okay, so V1 effective
cos of-
into IS effective into cos of theta minus phi. Okay, okay, you can use any of these two formulas, but remember when Vm you are using, you have to calculate the maximum value of the voltage which was given here. Okay, because in the question they have given RMS. Okay, that means effective value. So the 60 volts is the RMS value of your source voltage. Okay, obviously when you are using this one in calculating your source current, obviously the source current, this 12 volts, 12 is there na amplitude, so this is also your RMS value only, this is not the maximum value. The IS current which was shown here, which is 12 at an angle of minus 53.13 degrees, this 12 is the RMS value or the effective value of your current, it is not the maximum value. Okay, right, so you can use second formula, which is V effective into I effective into cos of theta minus phi straight away. Or if you want to use Vm Im by 2 into cos of theta minus phi, you have to multiply this 12 into root 2 and this 60 also with root 2. Okay, both will give you the same result. Okay, right, so I am using formula 2, which is Vrms into Irms into cos of theta minus phi. So what will be that? 60 into 12 into cos of, what is the phase angle of voltage? What is the value of theta here?
0.
Yeah,
0.
theta is equals to 0. Okay, so theta minus of minus 53.13. Okay, because your current has a phase angle of 53.13 minus. Okay, so that will be that. Oh, okay, V1, you have to use V1, right? It's not 0 because the source has 0 phase angle, but your voltage V1 has a phase angle of minus 79.7. So that's why you have to use that in this formula. Okay, so it is V1 into IS into cos of angle of V1 minus angle of IS. If you solve this, you are going to get 288 watts. Okay, is it clear? So this P1 is the average power consumed by load 1, which is 2 minus J1 ohms. Okay, is it clear to everyone how to calculate P1?
Yes, sir.
Or anyone has any doubt with regards to angle shown here? Any doubt? Okay, so P1 is this value 288 watts you got. Okay, the average power consumed by load 1. Next, try to calculate the average power consumed by load 2. That means 1 plus J5 ohms. How much average power it is getting consumed? Try to calculate that.
Sir, 651 watt.
651 watts.
Yes,
Average power consumed by load 2. That means
Yes,
1
sir.
plus J5 ohms.
Yes, sir.
Are you sure?
Sir, let me.
I don't think you will get 651. Please check it one more time. You have to calculate the voltage across 1 plus J5 ohms first thing. Current will anyway remain the same what you have already calculated. Then it will be V2 into IS into cos of angle of V2 minus angle of IS. That you have to do. Okay, I don't think it will be 651. Check one more time. Did anyone calculate P2?
Sir, V2 is 61.2, angle 25.56.
V2 60, how much?
Sir, angle is 25.56.
Sir, 144 watt.
Okay, so the average power P2 is 144 watts. Someone is
Yes,
saying.
sir, 144.
Okay, so someone is saying 144 watts. Did you calculate voltage V2?
Yes, sir.
How
So
much is
60
that?
at the angle of 25.56.
Okay, so something you got 61 point something 62 point. Okay, let's see that. So simply you have the source voltage of. Okay, anyway, I doubt that. Well, let's see. So you have source voltage of 60 at an angle of 0 degrees, and you know the voltage V1. Simply you have to apply KVL. Okay, so total voltage, source voltage minus this voltage V1, that should give you V2 value. Okay, right. So you got 61.18 at an angle of 25.56. Okay, this will be your V2. You got the same angle?
Yes, sir.
Yes, sir, same angle.
Okay, so now you have V2, you have the current flowing through that, so you can simply calculate the power P2. Okay, so what will be that?
144 watt.
So 144 watts. So how you have to do? Multiply 61.18 into the source current, I think 12, into cos of 25.56 minus of the angle of your current IS. Okay, whatever you got. Okay, so you have to do like this: 61.18 into 12 into cos of 25.56 minus of your angle for current is minus 53.13. So you'll get 144 watts. Okay, so this is the average power consumed by the second load. Next in the question they have asked, calculate the apparent power supplied from the source. So what will be that value? Apparent power? Simply VRMS. They are asking apparent power supplied from the source. That means across the source you have to know what is the voltage and what is the current coming from the source. Voltage across the source is 60 at an angle of 0 degrees. So 60 is your RMS value into current which is coming from the source. So IS. So IS has 12 as RMS value. So 60 into 12, that means 720 volt amperes is your apparent power. Remember, apparent power is always denoted with S. Okay, and it's only okay. Okay, so you remember that apparent power is denoted by S. Okay, so apparent power value will be 60 into 12, which is 720 volt amperes. Correct, na? Is it clear to everyone?
Yes, sir.
Okay, so now they have asked, I think they have asked the power factor of the source also. Try to calculate what is the power factor from the source. Apparent power supplied from the source, power factor of the combined load. So that means power factor from the source. What will be the power factor? What is the formula you have to use for calculating power factor?
Sir,
0.6.
minus 53.
You say lagging or leading? 0.6. So how you have arrived at 0.6? What formula you have used?
Sir, cos theta
432 upon
minus 5.
20.
0.196 reading, sir.
0.196 leading. Okay. Anyway, so what is the formula you have to use? What? Okay. So power factor from the source they are asking. So power factor from the source is equals to average power delivered from the source by apparent power delivered from the source. That means average power divided by apparent power. What is the average power delivered from the source? Can anyone say?
So 288 plus 144.
Yeah, that's correct. So it will be 288 plus 144 because the average power delivered from the source will be consumed by the loads. Or otherwise, you can calculate the same formula, average power from the source as RMS value of source voltage, RMS value of source current into cos of angle of source voltage minus angle of source current. If you do that also, you will get the average power. Apparent power is already known to you, which is 720 volt amperes. Okay, so simply you have to divide by both. Okay, right. So the average power or the real power supplied from the source. If you use this formula, you will get 288 plus 144, which is nothing but 432 watts. Okay, right. If you add up also, you'll get the same value. Okay, you can use any method to find out the average power delivered from the source. Then power factor will be 4 average power divided by apparent power, which is 432 divided by 720, which is 0.6 lagging. Okay, how I am saying it is lagging? Can anyone say what are the basis or on what observation I have told it is lagging?
Sir, because current is at angle minus 53.13 degree, and voltage is at angle 0 degree.
Okay, so since the power factor of the source they have asked, you have to see the voltage across the source and current delivered from the source. Voltage across the source, we have seen it as 60 at an angle of 0 degrees. Okay, so that means voltage is your reference phasor, which is at 0 degrees, and the source current is seen to be minus 53 so point something. So current is lagging, so that means your current is lagging the voltage. That's why I have called it as lagging power factor, and the value is 0.6. Okay, so is it clear? So the power factor is 0.6 lagging. Okay, so this is how you have to calculate the power factor, apparent power, or real power, whatever it may be. Right. Now I will ask any,
Sir,
any
you are asked complex power supplied from source means?
that we will discuss. Complex power is also there. Next slide will be on that. Okay. So we have seen what is power factor, average power, apparent power. Okay. Okay. So for calculating the average power delivered to the source, that means average power absorbed by this load 1, which is 2 minus J1 ohms, we have used this formula and calculated, which is observed to be 288 watts. Okay. Right. Can anyone say what will be this average power straight away by seeing this current and this load? That means using only this current value, which is shown here, 12 at an angle of minus 53, and seeing the load 2 minus J1, can anyone say what will be the average power?
I square R.
Okay, so what is that I square R value here? What is that I square R value here? Which is 12 square into 12 square into 2. So 12 square is 144 and into 2 will be 288. Okay, so that means when you know the current flowing and this is a complex value which shows that this is your R and this is your reactance. In this present case it is minus, so that means something like capacitive reactance here. Okay, so I square R into do, if you do straight away you can calculate the average power consumed by this load alone. Okay, right. But the method what I have shown is, I mean, step-by-step process which will not have any confusion. Clear cutly it will specify what is average power, what are the phase angles, everything. Okay, but if you have, I mean, good knowledge and if you have better understanding, you can use this method also, which is nothing but I square into R. Okay, right. So that will be 288 watts straight away. Similarly for second one also, which is 12 square into 1, which is nothing but 144 watts. That's what we have got here. Okay, 144 watts. So straight away by seeing the after calculating current also you can calculate the average power. Okay. So this is regarding this problem. Do you know any other formula for power factor in terms of R and Z?
R by Z, sir.
R by Z.
Power factor is cos phi is R by Z. So that okay. So this is called as impedance triangle, where the real axis will be your resistance and imaginary axis will be J into XL minus XC. Okay, right. So if you use this formula also, you can calculate the power factor. Okay, so power factor from the source they have asked na cos phi is equals to R by Z. Okay, so even that thing you can use. Okay, so what is Z here? 3 plus J4. So what is the magnitude of this one?
Sir,
Sir,
5.
5.
5. So denominator is 5.
5.
What will be the numerator? R value? 3.
3.
So cos phi is R by Z. So cos theta is equals to 3 divided by 5. Okay. So from that also you can calculate the power factor will be 0.6. Okay. Right. Only that value you can calculate, and from seeing this also you should be able to say this is plus J4. So obviously your power factor will be lagging. Plus J4 always indicates inductive nature load. Okay. Minus J, if I have something like minus J, then it is capacitive nature load. Okay. So from this itself you can calculate power factor. Cos phi is equals to R by Z. R is nothing but 3 and Z is 5. So 3 by 5, that will be 0.6. And if you have plus sign here, which means inductive nature load, so that is 0.6 lagging. Okay. So from this impedance itself, you can say the power factor value and what is the nature of the load also. Okay. But you require some amount of practice in this. Is it clear?
Sir, on load, sir.
Yes, sir.
Okay. So what is the doubt?
Sir, while using I square R, don't we consider the angle minus 53.13, sir?
I square R, huh?
Yes, sir. Sir, and that I means IRMS, no, sir?
Yeah. I means only IRMS. Angle we will not consider. Okay. So IRMS, I square R means IRMS square into R value. That's all. Okay. Angle will not consider, only magnitude.
Yes, sir.
Okay. Okay. Okay then. So we'll have a break of 10 minutes. Maybe 11:35 we will join back. Okay. Okay. 11:35 we'll meet. Bye.